Happy New Year. Today is January 1st, 2021, and this is our first lecture in quantum mechanics. And we ought to start with the preliminaries. What is quantum mechanics? Well, it's a more complete description of nature than classical mechanics is, as we might have studied through Newton's laws. How is it more complete? Well, it examines the realm of the very small, where Newton's laws fail. Right now, there's nothing better in terms of a theory to describe the very small. If we were to go a step further and study relativistic quantum mechanics, we could also study things that move at speeds approaching that of light. But for now, non-relativistic quantum mechanics will suffice. We can do a lot of good things with that. Why do we study quantum mechanics? Well, nearly every branch of physics utilizes quantum mechanics extensively. Examples: particle physics and field theory, statistical mechanics, condensed matter and condensed matter field theory, solid state physics, nuclear physics and atomic physics, and optics and lasers, just to name a few. In addition, all of chemistry is based on quantum mechanics as well. So the question is quantum mechanics the ultimate theory? Well, we're not sure yet. The one thing we do know is that it works. And one of the things that we hope to do throughout the course of this class is to enable you to solve a lot of quantum mechanics problems and make quantum mechanics work for you. Some caveats. Some people find quantum mechanics unsatisfying because it's a probabilistic interpretation of nature rather than a deterministic one, the way Newton's laws are. And so that probability and uncertainty, as opposed to determinism, makes some people a little bit uneasy. They hope that there would be a deeper theory that would come about to replace quantum mechanics, but as yet, none has surfaced. So you might ask the question, so will I understand quantum mechanics by taking this class? And I think that the answer, probably the best answer, is Richard Feynman's answer, the great Nobel laureate, who said, I think it's safe to say that nobody understands quantum mechanics. That being the case, as I've said before, as long as we can do quantum mechanics, we can get a lot of mileage out of this class, and it will propel us to many future classes and areas of research in physics. So our approach is going to be the following. Let's learn the basic ideas and principles of quantum mechanics and their uses, learn basic tools, techniques, and calculations in quantum mechanics, and practice them. In other words, solve a lot of problems. Ultimately, your ability to solve a number of different types of problems in quantum mechanics will be the judge of how good this course is. And of course, as we go along, we'll learn to ask the bigger questions. And at least if we end up confused, there'll be a good reason for it. The texts that we're using in the course will be two of them. First is the sort of standard Griffiths Quantum Mechanics, the third edition. This is a really good fundamental book on quantum mechanics. And the other I'm going to use this semester for the first time is Quantum Mechanics, the Theoretical Minimum by Leonard Susskind and Art Friedman. This is a different approach to quantum mechanics, but I think it is also very nice in providing insights in quantum mechanics to people who are just learning the subject. So, we'll be using those two books, mostly be doing problems out of Griffith's text. Where do we begin? Let's begin with light. At the turn of the century, that is to say the turn of the 20th century, from the 19th to the 20th, most scientists were convinced that light was a wave. In the early 1800s, Thomas Young performed a double slit experiment that illustrated the wave properties of light. And it worked in sort of the following way. Suppose we have a source of light and we have it shine upon two slits. What we're going to see are waves that emerge from the two slits, and you're going to see places where they interfere constructively and destructively. That is to say, if the peak of one wave interferes with the peak of another wave, we get constructive interference, and we'll get a bright fringe. And if we have a peak of a wave coincide with the trough of the other wave, we get a dark fringe. And so we have these alternating bright and dark fringes from the light, and that indicates that there is a wave-like property of light. Now, these results were actually rejected early on because Newton, the great Newton, had always pictured light and described light as a particle. He very much advocated the corpuscular nature of light. But in the 1860s, James Clerk Maxwell completed a unified field theory of electricity and magnetism and demonstrated pretty unequivocally that changing electric and changing magnetic fields produced what we call electromagnetic waves, which traveled at the speed of light. This time the speed of light was well known. And so it was fairly well determined that light was a wave at that point. Beyond that, Hertz was actually able to create and detect electromagnetic waves in the laboratory about 20 years later. And of course, that was the great confirmation of Maxwell's theory. So that brings us to about 1900. And while there were a lot of things that we understood about physics in 1900, there were still some nagging problems. One of them, well, there are a number of things, and we might consider them failures of classical physics and the classical atom. And we'll cover those in our next lecture.